All right, today is our first lesson in the second chapter. It's on radical functions, and what we'll be doing with a radical function is transforming it. So first off, you can see this blue graph is our radical equation, and if you can't remember, a radical is just a square root. So this blue graph is the equation y equals square root of x, and we can see the red one is some sort of transformation. We've reflected it vertically, we've shifted it over 2, down 1, and we've also done some sort of stretch. So for this topic, we're going to be looking at what the graphs look like and how we would do the transformations, much like we did in chapter 1. So first off, if you think back to chapter 1 when we're dealing with inverses, we had a quadratic, which was y equals x squared or some sort of graph like that. And if we did an inverse, remember it gave us a sideways parabola, but that wasn't a function. So what we did was we basically broke it apart and did the positive values to be one of them, so that would be our square root of x, and then we broke it into the negative values, which was our negative square root of x. So to keep it as a function, we had to do it as two parts. So with radical functions, then we're only going to use one, and typically we just use the positive, because if we wanted the negative version, we just do a vertical reflection, and that would put that negative out front, just like we were doing before. So y equals square root of x will be sort of our base function, and that's what we're going to be working with in this chapter. So in terms of the graph, let's make a little data table and plot a few points. So if x is 0, square root of 0 is 0. If x is 1, square root of 1 is 1. If x was 4, we get square root of 4 is 2. So we kind of skip the 2 and 3. You can see those are decimals. If we jump over to 9, we would get 3. And we can keep going to 16, we get 4, and so on. So you can see it just follows that pattern. We notice that you don't have a negative. We can't have a negative 1 because square root of negative 1 doesn't exist, so we don't get negatives. And if you had something like a fraction, you'd have square root of, say, a quarter, would actually give you a half. So a quarter would be somewhere in there. It would be about halfway up. So it works with decimals, fractions, but typically we'll just stick with the nice coordinates, the 1, 2, 3 coordinates, then we don't have to worry about decimals and fractions and that type of thing. So when we're doing our transformation now, what we're going to do is we're going to take that square root of x equation and transform it by doing a vertical stretch or reflection. So just like before, our number out in front, so our a number is going to be the stretch. So if you had a 3 out front, it's going to be 3 times taller. If it was negative 3, that means we flipped it vertically and then times it by 3. The b number inside the square root will be just like we did before, where we've got to do the reciprocal. So if the b was a 2, that means we'd have a half stretch horizontally. And if it was negative, then once again we'd have a horizontal reflection. Our h inside the brackets with the x is left or right. Remember to do the opposite. And k outside is our up or down, and you can leave it as is. So what's important with this equation when you look at it is it's pretty much the exact same as what we had before. So I'll refresh your memory here. If we did our old equation, we had AF of BX minus H plus K. So if you compare the two, you can see it's pretty much exactly the same thing, except the square root kind of replaces the generic function. So where we had F, that is where our square root is now. But you can see, other than that, it's pretty much exactly the same thing. So once again, you can rewrite it like we did before. If you would rather have the k with the y, you could do that. You could write it as y minus k on the one side, and then AF bx, or sorry, we don't need the f. It would be a square root bx minus h. So you could write it like that, and that kind of shows us why at the bottom here we want to make sure we don't put the k under the square root, because it's attached to the y. We can see it's dealing with the y translation, not with the x, so we want to keep the x one under the root, but keep the k one by itself. Okay, so let's go through an example where we draw the transformation. But first of all, let's figure out the transformation in terms, and then we'll draw the graph afterwards. So we've got this negative 2 out front, so remember the negative will be a vertical reflection. And then the 2 would make it vertical stretch times 2. Okay, so let's draw that for this graph. So Let's stick with our easy coordinates, our 0, 0, 1, 1, 4, 2, 9, 3. That's good enough. So let's do our vertical reflection. Those will go downwards, so that one will drop down, this one will drop down, and our 9 will drop down. So our vertical reflection would look something like that. We want a vertical stretch of 2. So let's get rid of that line, and let's times it by 2 right away. So we'll double our vertical height, so that'll go to -2, this one would go to -4, and this one would go down to -6. So there's our -2 taken care of. Now we got to do the same thing for the 4. So the 4 inside the root this time, remember that'll be a horizontal stretch, but now that's going to be horizontal by a quarter. So we take all of our x coordinates now and move them over to a quarter the size. So if it's at 1, it's now going to be at a quarter. This one's at 4, it's going to move over to 1. And the 9 would be about 2.25 or something like that. So you can see our horizontal does that. And then now our last step is deal with the translation. So we'd have 3 right and 1 up. So if we just take every coordinate on our blue line and move it 3 right and 1 up. So take that origin, go over 3 up 1. Take this one, go over 3 and up 1. And our last one, over 3 up 1. And we get the idea. So there's our transformed graph. And if we needed to, just like we did before, we could then figure out our domain and range. So on our original graphs, our domain was x is greater than 0 and y is greater than 0 for the range. So now we can see that actually changed. Our domain now is x is greater than 3, and our range, we're starting at +1 and going downwards, so now our y is less than or equal to 1. And if you look at the domain and range, you can see those numbers are basically changing whatever our translation was. We started at the origin, the 0, 0, but we went 3 right and 1 up, and we did a reflection, so that sort of takes care of these numbers. So our 3 run comes from that, and our changing of from greater than to less than was because of that vertical reflection. And that's it. So you can do it that way, sort of work with the graph, do each step if you want. Or the other option that some people like is just dealing with coordinates by themselves and sort of translating each coordinate one at a time. So if we take these coordinates, that's our basic ones again. Let's plot them first. So 0, 0, 1, 1, 4, 2, and that's good enough. So there's our original graph, something like that. So now let's go back and actually translate these. So the 4 in the equation means we're doing a 4 times vertical stretch. So that means we're actually just timesing the y coordinate by 4. So we can just do that with each coordinate. So 0 times 4 is still 0, 1, 4, 4, 8, and our last one will be 9, 12. We times each y coordinate by 4. Now if we take care of the -2, you can see that we would get a -2, which is a horizontal reflection, but we also make it a half because of the horizontal flip idea. So let's just take each x coordinate and times it by -1/2. So we still get 0, 0, -0.5 and 4, -2 and 8, and our last one would be -4.5 and 12. And then our last step is do the translation. So we've got 3 left, and our -5 would be 5 down. So we just do that on the last one. So take each coordinate, go 3 left, we'll make it -3, 5 down would be -5. Do that with the rest, -3.5, and -1, -5, and 3, and -7.5, and 7. So we've done all of our translations now, so all we have to do is plot those final coordinates, and we should be good. So -3, -5 would be there. Our next one is -3.5 and 1. So that's there. Then we had -5 and +3, which is about there, and that's good enough. The other one's kind of off the chart. So you can see that there's our transformation. And once again, if we needed to do domain and range, so you can see our x now in this case we're going less than -3. And our range would be y is greater than or equal to 1, 2, 3, 4, 5, -5. And we're done. So whichever method you like, some people like working with the graph, other people like working with coordinates, but you'll get the same answer either way. And our last example now is how do we get the equation from the graph. So in this case I've got a graph, we can see that it's been shifted over and stretched and all that. The hard part is how do we get the equation. So a good strategy, first of all, is figure out the translation. So you can see our origin is now moved to 4, 2. So we know that we went 4 right and 2 up. So in terms of our equation, we can actually put that in there because we know we're going to have some sort of x. 4 to the right would be -4. And we got 2 up, so we'd have +2 on the outside. So we know that that's been taken care of. So now all we have to worry about is what the stretch is. So because we kind of dealt with the transformation, the easiest way to do these, instead of trying to look at weird coordinates, is why don't we just redraw this where we imagine the origin being where it was after it was translated. So if you just sort of kind of redraw in a grid where it's starting at the origin, now we can figure out our stretch pretty easily. We have no reflection, because if it was reflection vertically, this graph would be upside down. We don't have that. If it was reflected horizontally, we'd have it going backwards. We don't have that. So we're pretty good in knowing that all we got left is to figure out the stretch. So remember, let's kind of plot in our original graph again. If we started at the origin, it would go over 1, up 1, and then we'd go over 4. So 1, 2, 3, 4, up 2. Over 9, 5, 6, 7, 8, 9, and that'd be up 3. And that's what our original graph would look like if we did that transformation, that translation of 4 right and 2 up. So what we want to do now is just compare where does the graph change from this blue one to the red one. So if you look at the blue one, we know we should go over 1 and up 1, but in reality, we've actually gone over 1, but we've gone up 3. So how do those compare? Well, we went vertically 3 times bigger. So that means if we use that logic, we should have a 3 times vertical stretch, which means we just put the 3 out front. And we're finished. So we could even kind of compare this for another one. Let's go over here. We have a distance of 2 originally. We now have a distance of 6. So we went from 2 to 6, so it is also 3 times bigger. And we could go from 3 to 9 and so on. We could keep doing this and we'd see that we're just getting 3 times taller for each coordinate. And we're finished. But with these kind of graphs, sometimes you won't know whether you're doing a vertical stretch or a horizontal stretch. It just depends on sort of your perspective. So with this last one, let's kind of redo this one again. But let's think of it in terms of a horizontal shift instead of a vertical. So if we look at this one again, our original was 1, 1. And then our original was, for the second part, we had 4 over and 2 up. And then we had 9 over and 3 up. So we're going to work with that 9, 3 because the rest of them would be kind of hard to read. But if we look at the 9, 3, you can see that this 3 location has actually been shifted over to there. We've done a horizontal compression or shrunk it. And we went from a distance of 9, but now we're at a distance of 1. So we've sort of taken this graph and went 9 times smaller, or 1/9 of a stretch. Okay, so we sort of compare this just like we did before, but instead of going vertical, instead of going 1 over and 3 up, we can think of it as being 9 over and 3 up, and now we've shrunk it down to 1 over and 3 up. So if we were to do it that way, with a horizontal stretch, we'd write it as square root 1/9. Because we're going smaller by 9, that would be 1/9 of a stretch. So in the equation, we'd write it as 9. And then we'd have x minus 4 plus 2 again. That didn't change. So if we compare these two graphs, this one is a 3 times vertical. This one is a 1/9 horizontal. But either one works. They both would give us the red graph that we want. And if you kind of look at the two equations, you can see they are actually the same equation. because in this case with that square root of 9, we could do that, and that would give us a 3 outside the root. So if we simplified that, we would get exactly what we had for the vertical. So what that means is with any of these kind of graphs, you'll get a vertical stretch or a horizontal stretch. Either one would give you the exact same equation and the exact same graph. And that's all.